Hello, this is Anna,
And this is Alia,
and this is Lab 1 for 471B.
Kinematic Design and Beam Alignment. This week in the lab, we are exploring various methods for optical alignment using different kinematic mounts. Kinematic design in optical components is integral to laser alignment because it dictates an engineer's ability to perform fine adjustments on an optical test bench. Accuracy is of the utmost importance when measuring and collecting data as a scientist or engineer, so learning these alignment techniques is essential to the future of our lab experimentation.
To verify the alignment, we use a pinhole method. We begin by positioning the pinhole close to laser output and adjusting its position to ensure the beam passes through without being clipped. Maintaining the pinhole's diameter, we first align the laser by translating it along the X and Y axes. As we gradually move the pinhole further from the laser, any residual misalignment becomes more apparent. At this stage, we fine-tune the laser's tip and tilt. It's crucial to avoid adjusting the tip tilt when the pinhole is too close to the laser, as this would create extreme angles that become much harder to align properly at greater distances. Once the laser beam consistently passes through the pinhole along the entire rail, we can confidently confirm that both the laser and the rail are properly aligned.
Now that our laser is aligned, we are going to test the levelness of our optical test bench. We have placed a pentaprism perpendicular to the optical rail. This way, we can ensure our beam will be pointed down towards the table. The pentaprism is important because it consistently deviates the beam by exactly 90 degrees regardless of slight misalignments, which make it a great tool for accurately directing the beam perpendicular to the optical path. Now we place a cup of water so that we can observe the back reflection onto the laser output plane. If we had a perfectly flat table, we could see the light return to the output position of the laser. The angle we observe is significantly misaligned, meaning the table isn't perfectly flat.
Now we are going to explore differences between the beam splitter and pentaprism alignment. We placed a pentaprism in the path of the beam and saw a 90-degree deviation of the beam. Then we replaced the component with a beam splitter. If the beam splitter is perfectly placed at 90 degrees, we should observe the beam at the same position marked previously. One key difference between the two components was that the pentaprism consistently deviated the beam by exactly 90 degrees, regardless of the slight misalignments, whereas the cube beam splitter was more sensitive to alignment and required precise positioning to achieve the desired beam paths. It's very hard to pick which one we preferred. The pentaprism is nice for predictable deviation angles and insensitivity to small misalignments. However, the cube beam splitter was useful when we needed to create two beams traveling at 90-degree angles simultaneously.
The next part of the lab was to co-align two visible laser beams. To do this, we set up a green laser to be parallel with the red beam and the optical rail. We used the same pinhole method described earlier to ensure that the beam was aligned. Lucky for us, we had the pinhole used in the earlier alignment and the height was untouched. So we knew that as long as the green laser was aligned using the same pinhole used in the red laser's alignment, then the height and parallel properties were the same. When co-aligning two beams, ensuring they are parallel is crucial to maintaining beam quality and preventing spatial separation over distance. Non-parallel beams can lead to phase mismatches, interference distortions, and reduced coupling efficiency in optical systems.
Now that they are aligned, we move on to overlapping their outputs in space. We introduced a cube beam splitter into the path of the red laser and adjusted it until two red beams exited at 90-degree angles from each other. We then placed a flat mirror in the path of the green laser to redirect it at 90 degrees toward the beam splitter. By fine-tuning the mirror's translation, we positioned the green beam so that the two distinct green dots appeared on the screen alongside the red dots. Finally, we adjusted the tip tilt of the mirror to bring the green beam into perfect overlap with the red beams, ensuring precise alignment. Using these fine adjustments, we could see the red and green dots become a single orange dot on 2 points in space. The mirror mounts used two adjustment screws, allowing for rotational adjustments about the Y and X axes.
The next part of the lab was aligning optical components. To construct the Keplerian telescope, we used lenses with focal lengths of 400 and 200 millimeters. To ensure precise positioning, we mounted the lenses on a micrometer stand for accurate translation. We began by individually aligning the 400 millimeter lens, estimating its center, and using 3 degrees of freedom to align the back reflected beam with the laser's output. This process involved constraining translation along the Y and Z axes and rotation about the Z axis. Once the 400 millimeter lens was properly aligned, we placed the 200 millimeter lens on the optical rail, positioned 60 centimeters in front of the first lens, and repeated the alignment process with the same degrees of freedom. The resulting system produced a magnification of 2, as the magnification of a Keplerian telescope is determined by the ratio of the focal lengths.
Now we are going to propagate the red laser through a microscope objective. We first used a magnification much too large to be useful for alignment, and we weren't able to observe any crosshairs. Once we switched out the 20 times to a 4 times objective, we were able to systematically align the magnified laser output with the crosshairs on the objective. We align the height of the microscope to allow the laser beam to travel through it and see a magnified beam on the other side. When the beam is aligned with the microscope, the crosshairs will remain in the center of the beam as you translate the microscope up and down the optical rail, and the beam will stay close to the starting location, which is shown as the dot on the sticky note. We did this by consistently adjusting the tip tilt of the mount to move the crosshairs of the microscope and translating the mount to move only the beam.